Hello students. Hello.
Good morning, sir.
Good morning everyone. So I'll start with the lecture. We are still at the chapter we are still at the chapter 2, that is magnetic field of the magnetic material, and we now go to the topic on the boundary conditions of the magnetic field vector B, and that is magnetic induction vector B and magnetic intensity vector H. So we are finding the boundary conditions on the magnetic field vectors B and H. Now this was similar to what you have learned in semester 5 in the electrostatics. There it was the boundary conditions on electric field vector E and the displacement vector D, E and D. So here also we go in the same line. You will find that the format of the derivation will be similar. And what we are doing here is, suppose there are two magnetic materials of the two different properties. Two different properties means what? In the two different materials, the value of the field is different, direction of the fields are different. Fields means B as well as H. So they have a different properties. Now at the surface separating the two, now what will be the value of B and H? See, in the two different media, the B is different and H is different. But at that, since the two media are touching each other at the interface, that means surface separating the two, what will the value of B and H? So that is what we want to find. So first, what I will do is, I will find the boundary condition on the magnetic induction vector B. So, uh, and here, if you see this diagram, now this is the interface. This is the interface. That means surface separating the medium 1 and medium 2. So there are two media, medium 1 and medium 2. And we take that each of the medium is isotropic. Isotropic means if there are two different physical quantities, their directions will be same. Isotropic. Iso means same. Tropic means direction, orientation. So here you find that the direction of vector B2 and direction of vector H2 is same. They are parallel. See, this is parallel to this. Similarly, in the medium 1, vector B1 is parallel to vector H1. So direction is same. But if you see the two different media, the direction of B1 is different from direction of B2. Direction of H1 is different from direction of H2. So we consider here the isotropic media. Then, so first we'll find a boundary condition for this magnetic induction vector B. What is the boundary condition? Means what will be value at this interface? See, the value in the medium 1 is B1 and value in the medium 2 is B2. But where at the surface separating the two, what will be the value? That's what we want to find. So to find out, we consider the pillbox. Pillbox. Pill means a tablet. So it is like a tablet. This tablet is a cylinder, but height is negligible as compared to the diameter. So that's why it is called as a pillbox. It is a closed surface. See, this S is the closed surface. It is closed on all the side. And if you see, there are three different surfaces: top circular surface, bottom circular surface, and this side there is a curved surface. Now we are going to neglect this surface because its height is negligible. It is a pillbox, so height is negligible. So we are going to neglect this surface. So we have to consider only the top surface and the bottom surface. As far as now area of the top surface and the bottom surface is delta S of both the surface, they equal area delta S. Now since this is a closed surface, the direction of the area vector is perpendicular outside. So on the top surface, perpendicular outside means upward, and bottom surface, perpendicular outside means downward. And we write here a unit vector. This unit vector of that area, and in the medium one, we call it is n1 cap, and it is directed downward, and on the top surface, it is unit vector n2, it is directed outside, so it is on the upper side. Then to this full surface, we use this Gauss's law. According to the Gauss's law in the magnetostatics, I'm not saying electrostatic, according to Gauss's law in the magnetostatics, that the surface integral, this is a surface integral over S, surface integral of the magnetic induction, surface integral of the magnetic induction. So since surface integral, this element is there, vector ds, we have written as n cap ds, and that is equal to 0 because the magnetic flux, magnetic field lines form the closed loop, so other side is 0. So if you take in the magnetic field any closed surface, that the total flux will be equal to 0 because lines comes out as well as enters the surface. Now this, we split this integral, it is addition, integral means addition. We take it for three parts. One is the upper circular surface, then the lower circular surface, and this curved surface. Now this curved surface will neglect because height is very negligible. So for the upper surface, we write this vector b2, vector b2 because magnetic field is b2, then vector n2 because it is in the medium 2, and into the area of that top surface is delta s. So vector b2 dot vector n2 delta s. Similarly, plus for the medium 1, it is vector b1 dot vector n1 into delta s. That is area. Area of the both the surfaces are same. So here the unit vector is vector of a area is vector n1, and here unit vector is n2. So we will take this like this. Then this delta s cancels. It cancels. You get like this. Then see this n2 and n1, they are oppositely directed. So n2 equal to minus n1, or n1, this n1 is minus n2. Now sign is minus because they are oppositely directed. Now if you try to evaluate this, it is say it is a dot product a dot b, vector a dot vector b, ab cos theta. So it will be in this case b2, then means magnitude of b vector b2, and magnitude of vector n2 is 1. It is 1 because it is a unit vector. Then cos of angle between these two, b2 and n2. See, this is the angle. This is the angle theta 2. So that is the angle b2 1 cos theta 2. So similarly here it will be b1 cos theta 1. For second part it will be b1 cos theta 1. Now if you look at this quantity b2 cos theta 2, so this b2 is in this direction, and this theta 2 is angle made by b2 with n2. So b2 cos theta 2 is nothing but the component of b2 in the direction of n2. So what is the component? See, if you take vector a, then component in making angle theta is a cos theta, perpendicular to that is a sin theta. So here this b2 cos theta 2, that means b2 in dot n2 is nothing but normal component of the magnetic field b2. So we have written here this 2n. So n means normal component. Similarly, this quantity is a normal component of b1 in direction of n2, that is b1n. And when you simplify this, b2n 2n equal to b1n. That means the normal component, see, the normal component of this b2 and b1 are equal. So at the surface, we have shown that normal components of magnetic induction vector B are continuous Continuous means they have the same value. Continuous across the surface. So this is what we have proved. This is a boundary condition for magnetic induction vector B. So if there are two surfaces, now this two mediums, in fact one medium can be a magnetic material, other medium can be a vacuum. At the surface, the values of magnetic induction vector will be same and normal components will be same. The value of the vector B2 will be different, but normal component will be same. Next, we go to the boundary condition. The boundary condition of magnetic intensity vector H. Magnetic intensity vector H. So now here again we look at the diagram. We take here this loop A, B, C, D, A. It is a closed loop, just imaginary loop, imaginary path B, A, B, C, D, A. Now, why have I taken here a closed path? Because we have to apply the Ampere's circuital law. This Ampere's circuital law we have to apply it. So we require a closed path, what is called the Amperean loop. And in this path again, we say that the CD and BA is negligible. So we say that it is negligible. Value is very low. So the component along that will be 0. Then length of this BC and length of that AD is delta L. Then we have denoted here vector I0. This vector I0 is not a current. It is just a unit vector. See, it is a unit vector of this delta L. So it is a unit vector corresponding to this length delta L. So that is called as a vector I0. Now let us apply the Ampere's circuital law to ABCD. This according to Ampere's circuital law in terms of the magnetic intensity. So Ampere's circuital law in terms of the magnetic intensity. This line integral of magnetic intensity vector. So this is the line integral. So of the this intensity vector. Then here what happens is in integrand that element should be there. So here the line element. So line element dl is the line element. Integrand has to be a scalar quantity. So we take a dot product. Now that is equal to that current enclosed. See, this is enclosed current. It can be written in terms of current density. So surface integral, this is a surface integral of that current density dot n cap ds. In fact, this n cap ds is nothing but a vector ds. So it is a vector that element area, vector of the element area. This is there. Now what we'll do here is we'll try to split this into 4 parts. Now along this CD and BA, it will be 0. So along this path BC, B to C, see B to C, this will be H2. Then the length here is delta L, but we have to write it as a vector quantity. And here what happens is only H2 is there. So that we multiply by unit vector I0. This is there. And then take a dot product. Then for this, see, you have to go in a closed path A, B, C, D, A. A, B and C, D we neglect because that length is very small. Now B to C, direction of vector I0 is along BC. Then this from D to A, the I0 is direction opposite to the D to A. So here what we do is, we write here minus sign. This minus sign is written because the direction of that length vector, see direction of this length vector here, direction of this length vector is, it is in this direction. So it is opposite to that of the I0. So minus sign is written. Then on this side, see now here what happens is, we are doing it at a surface, So now this vector small j is a surface density, Okay. So now here, this to give the direction to that surface density, we take N2 cross I cap. See N2 cross I cap, vector I0. So that this lies in along the surface of this. It is a surface density along that interface. So then we take J dot N2 cross I naught, and then if you see this is a scalar triple product, and in scalar triple product is a cyclic. So we can replace interchange the dot and cross. So what you get is J cross N2 dot I naught. Then this you can cancel this I naught. You can cancel this I naught. That is one thing. Then if you see this H2 dot I naught, see H2 dot I naught. This now this angle. See now in fact what you will get is this angle is theta 2. This angle is theta 2. So now in this H2 dot I naught means here H2 is in this direction and I2 is in direction. So this H2 dot I naught is in the direction of this I naught. That means along the surface. So that's why we call this as a tangential component. We call it as tangential component. So H2T, T means a tangential component. So in fact it will be H2 sin theta, and here it will be H1 sin theta. So in fact here if you evaluate this, you will get H2 sin theta 2, sin theta 2. So that is a tangential component. Then on the surface, see there is no density on the surface. On surface, then surface density is 0. Surface density is 0. So J is 0. And what you get here is H2T equal to H1T. That means at the surface, the tangential component, that means component of this H2 in the direction of the surface, are continuous. Continuous means they have same value. So these are the boundary conditions on the magnetic intensity vector H. Now exactly similar way we have done it in the electrostatics, but that was done for the dielectrics, electric field vector and the displacement vector. Next we will go to a current circuit containing the magnetic meridian. Current circuit. So current circuit is there, but inside that circuit some magnetic material is there. And here we take the toroid. Now this is a toroid. See what we consider here is the toroid. A toroid is nothing but you take a spring and bend it into the circle. You take a spring, you bend it into a circle. If you take a spring like this and if you pass a current, there is a straight solenoid. And if you bend it into a circle, it is a toroid. Then, now normally what is done is, this winding is done. See what is done is, a ring is taken like this with a small gap. Metallic ring is taken. In fact, a ferromagnetic ring is taken with some gap. This is the gap. So this is the gap. Gap is there. So ring is taken with the gap. And around that, a winding is done. Around that, winding is done. Okay, so now what happens is, see what happens is the current is flowing like this. And you will find that inside there is a magnetic field. See this toroid will produce the magnetic field. Then the magnetic field produced by the toroid is always perpendicular to each and every loop. These are the loops. So toroid is nothing but loops placed in a circle. So the loops placed in a straight line, that is a solenoid. The loops placed in the this circle, that is called as a toroid. So direction of magnetic field is perpendicular to the loop. Now you can consider the path like this. I have shown here dotted path of the radius r. I have taken the dotted path, and you will find that direction of magnetic field produced by that toroid will be in this, tangent to this. Then direction of H will be also tangent to that circle. So now we'll to this circle for this loop. So now this is the Amperian loop. So to apply the Ampere's circuital law, we have to consider the Amperian loop. To this Amperian loop, we'll apply the Ampere's circuital law. So this circular loop. So now what is drawn here in dotted line, that is the this Amperian loop. It is a path. So it is a path, but it is a circular path. It is a circular path. And to this, according to Ampere's second law, that line integral of vector h is equal to surface integral of vector j. Then this h dot dl is, see, the h is, all h is tangential. So I have written here h suffix t dl. Then now, as I mentioned earlier, that the magnetic field, magnetic intensity is perpendicular to each and every loop. So it will be tangent to this loop. Then the dl is an element of this loop. So it will be also along that tangential to that loop. So angle is 0. See, cos of 0. H dot dl is ht dl cos 0. Because direction of h is tangential to that circle. Direction of dl is also tangential to that circle. And on the other side we get vector j dot nk ds. Then now this at each and every point, see, inside that toroid, the magnetic field and magnetic intensity is uniform. If the value is same, so if the value is constant, comes out, what it remains is line integral of dl cos 0 is 1. Now this is equal to 1. And on other side, now this quantity is nothing but current. See, vector j is a current density, current by area into area, that is the current. Now, as we have mentioned earlier in Ampere's circular law, now this is what is called as the enclosed current. So current is crossing. So example here, this is the loop, this is a circular loop. Here what happened, the winding is there. So current is crossing once, current is crossing twice. So there are n turns, current is crossing n times. See that in that Ampere's circular law, that current is a total current crossing that loop. So here what happened, around this circle, it is looped. So in one loop, the current will cross that area once, second loop, second time, third loop, third time, and in the n loop, n times. So here, what we do here is, this integral, the cos 0 is 1, integral of dl is L. L is a total length, because integral means addition. You add each and every element, you get a total length. So this is L. Then this total current which is crossing that loop, the current I is flowing here. It is crossing n times because there are n loops. So it is Ni. L is 2 pi r. L is 2 pi r. You can write it in that terms of that. So if it required, we write it later on. But here we write it as h suffix t. T means it is a tangential component of that magnetic intensity, Ni divided by L. So n by L, see this quantity, this n divided by L, number of turns per unit length. See, over this length, total number of turns are capital N. So n by L is total number of turns per unit length. So we get h suffix t equal to Ni. So here I was mentioning that earlier, that the magnetic edge is something to do with the external. See, if there is magnetic material inside, the current through this is responsible to produce the magnetization in that material. That's what I had mentioned. So here we have proved now that H equal to Ni. So that what is called magnetic intensity entirely depends upon the this current flowing through that solenoid. It may be toroid or solenoid. Same thing will apply here. Same formula applies here. So H equal to Ni. So this is what we find in the current circuit containing the magnetic media. We'll go further. This we have already defined. H we have already defined. H we have already defined in earlier part. 1 by mu naught B minus M. Then you simplify this. Simplify this. Mu naught, it multiply by mu naught, and take this minus mu naught M on the other side become plus mu naught. You get this. Now we can split this into two components. See, suppose you want to find magnetic tangential component of magnetic induction. So this first part, if you see the first part, this part, mu naught Ni by L, and here this quantity entirely depends on the current. So we call it as, because of a transport current. This quantity we call it as a transport current. So because of a transport current. So first term is because of the transport current. Because transport current means current flowing through that toroid or straight solenoid. Same thing can apply for the straight solenoid. Then the second term, if is second term, it depends upon the magnetization of the material inside. So magnetization of the material inside. So now what happens is there is some correction here, and mathematically using that trial and error, they have found the correction. So normally what happened is the full ring is not taken, but see the ring which is taken with a small gap because it is required for winding. Otherwise, if you take a ring, the winding will be not possible. To wind it, what is done is a gap is kept there. So in fact, it is done with the machine. So if there is no gap in that ring, then what happens is the winding will not be possible. Now this is the length of that gap. This is the length of that gap. This is D. Now here what happens is, in this gap, there is no material. So material is there in this part. Inside the solid and material is there, but in the gap there is no material. And by trial and error method, see some correction is applied. In physics, we apply the correction. Normally correction, it is done by what is called the empirical method. Empirical method means trial and error method. In many cases, we apply the corrections. Then this for small gap, it comes like this. M into 1 minus D by L. M is the magnetization of that material, and 1 minus D is that length of that gap, and L is the this length of this ring. Then we open this bracket, and here we find that this, when we what is there is only M. M is because of the magnetization of this magnetization of this gap, because there is no material in the gap. There is no material, and this second term corresponds to magnetization of the material. So this actually we cannot prove it mathematically, but experimentally by trial and error we can show that. So in the material, see H2 is in the material. In the material, that intensity is minus M D by L, and in the gap it is M. So this is about the current circuit containing the magnetic media. So I will stop here, and next time I will take what are called as the magnetic circuits. So next time means it will be on the Saturday. Tomorrow I will not take the lecture. So on Saturday I will take these magnetic circuits. Then we will derive the basic magnetic circuit equation, and then we will take up the magnetic circuit containing the permanent magnet. So that will be done on Saturday. So with this I halt for the lecture and continue on the Saturday. Thank you very much.
Thank you, sir.
Thank you, sir.
You're welcome.